two sections of the chapter, so it's not too much. And even though this is so this is going to be about wave optics, and we are going to cover only two sections: Young double slit experiment and the analysis model for wave interference. Okay, actually optics is very interesting field because we see in color, and it would be very nice that we understand why we see colors and how and what are the physics of the waves, electromagnetic waves, whether it's light or X-rays and so on. Everything around us, in fact, most of our communication devices work based on propagation of waves. So this is a very important and interesting physics topic. So you will just look at the surface of it, but if you are interested, you can study it further. Okay, so let me start with the demo. Okay, so this is an experiment.
This is a demonstration of the pattern you get when you send light through two slits. In this demonstration, I've got a laser here. I'm sending it through two slits that are separated in the first case by 0.25 millimeters, and then in the second case by 0.5 millimeters, larger separation. In both cases, each of the two slits is 0.04 millimeters wide. So what you see now is the pattern produced by this two-slit pattern. And you can see a big bright spot here, but I'm hoping you'll be able to see that there are small divisions, maybe 10 or 12 divisions within this big bright spot. Those are produced by the fact that we have two slits, interference, both constructive interference and destructive interference through this region. You can also see it divided out here in the other bright spots. So if we move to doubling the separation to 0.5 millimeters, then a wider separation means tighter spacing between those interference fringes. So you may or may not be able to see on the screen now that this main maximum is still as wide as it was before, but there's double the number of individual divisions within it. So the actual pattern that you can see right now is the single slit diffraction pattern for a single slit with 0.0.
We'll stop here and let's explain what we just have observed. Okay, let's go to presentation mode. Thank you. Okay, so here we have a wave laser coming to two slits. So these are opening. This is a screen that blocks the light waves except these two openings. These are called slits. The separation between the two slits is this T. Okay, and when the light comes to the slit, it will diffract, okay, at different angles. And if you put the screen far away from the slits, you get what we call fringes. So what you have, for example, this here corresponds to maximum intensity, but here this corresponds to minimum intensity. So where we have maximum, we call it constructive interference. Constructive waves are in phase. And here, when you have a dark region, this is what we call a dark fringe. This is called destructive interference. The waves cancel each other. That's why you get a dark spot. Then you get a bright spot, a dark spot, and so on. So these are called fringes. Okay, this is the maximum here, where you have bright region, and you have a minimum and the dark region. Okay, so this is what we just have observed. Okay, and this was originally done by Thomas Young in 1801. Okay, And so this is a very interesting experiment. Okay, so we said at the bright spots we have constructive interference, and at the dark spot we have destructive interference, because the waves cancel each other at that location. Okay, so let's see here. So here we are illustrating this. Okay, so let me run this simulation here. So here we have a laser source. You can control the wavelength. You can use blue laser, green, or whatever frequency. You can also control the amplitude of the light. These are the two slits. Okay, and so the wave is originally a plane wave traveling, and when it reaches here, it diffracts at an angle. So here you can see the wave was a planar wave. Now it's like a spherical wave here and here. Okay, and this is a screen far away from the two slits, and you can see on the screen we have a bright spot here. This is where we have constructive interference, and we have a dark spot. This is where we have destructive interference. In fact, let me move. So here I have two detectors. One detector here that is measuring this sine wave, and I have a detector here on the screen. I can move around to show you where we have constructive and destructive interference. So now you can see, if I am in the middle, you can see that we have now the two waves. They give us a maximum, which is a constructive interference. But if I move it away from the center, notice that I'm reaching a region of destructive interference, and normally I should reach an area or a place where the amplitude is minimum. I cannot exactly do it, but you can see. So now we have totally destructive interference. You don't see what we measure here, because we have the two waves cancel each other. We are at this spot. The intensity is minimum. That's where we have destructive interference. Okay. The nice thing here, you can vary the frequency of the source. You can vary the distance between the slits. Okay, and you can vary the width of the or the slit separation and the width of the slit. So when we do that, it will affect. So let's say, for example, here you can see that the slit width. Now we see we have a different pattern. So and if I the slit separation also has an effect. So you can see if I vary the slit separation, the pattern that we get on the screen is different. So all of these parameters are affecting the interference pattern that we are observing. Okay, so let's see. Stop it here and go back here. Okay, all right. So what is happening at this location? Let me use my okay. So we know that these waves are sine waves. Okay. If you are at a point O, originally at point O here, you can see that the waves are arriving at the same time in phase. So the amplitude of wave 1, let's call this is wave 1, this is wave 2. When they arrive here, they arrive at the same time, and that's why we have maximum intensity, because there is constructive interference. However, so here is another point where they also arrive in phase, point P. Okay, you can see this is wave 1, wave 2, and also they arrive at point P in phase, and you get a maximum intensity at that location. However, point R, which is halfway between P and O, you can see when the waves arrive here, one wave is maximum and the other one is minimum, or they are opposite signs. So they cancel each other. It's like a sign and inverting the sign, and you're adding them, you get 0. Okay, so this is where we get a dark fringe. All right, and if we want to illustrate this, so here, so if I run this one, okay, so now this is two slits. These are two sine waves. They arrive at the same time at this point here, because the same distance. But if I move Y, so let me move Y So here also they are arriving in phase. They are arriving at the same time, so we still have constructive interference. But let me go to somewhere in between. You can see now the waves are arriving. They are out of phase. So one cancels the other. That's why we get a minimum in this experiment. In this experiment also we can vary the wavelength of the laser source. Okay, we can vary also the distance L between the slits and the screen, and we can vary the separation between these two. So we can run this experiment and you see the effects of all of these parameters on each other. So let's look at the math. Okay, so we just have explained this. All right, so in order to observe this interference pattern, if we perform an experiment, there are two conditions we have to have. The two sources, or the light coming from the two slits, must be coherent. That means they contain constant phase with respect of each other. So the two sources, they are in phase, or it's the same source, the same laser light, and you put a slit. That means as if you have two sources of light. The slits are now two sources of light, and they are coherent. That means they are in phase. If one is sine, the other one is sine also. They are in phase. The second condition in order to perform this is that the source of light has to be monochromatic, meaning it has a single wavelength. It's not a spectrum. Like the white light is a spectrum of frequencies. A monochromatic light, like laser, red, blue, or green laser, it's single frequency and single wavelength. So you have to have a monochromatic source in order to perform this experiment. So you have to have a monochromatic source, and you have to have the coherent light from the two sources. In this case, it's because we're using only one laser, and when it arrives at the two slits, first of all, laser is coherent. It's single frequency or single wavelength. Second, when it arrives at the slits, they are coherent. They are in phase. Okay, so this is how we can perform this experiment. Instead of using two sources of light, we can use a single source of light, S. Okay, far away. The waves now will be traveling in a planar wave, and you make a slit. So now, as if you have two sources of light, and they're emitting light in all directions, and that's how you can get the interference pattern. You get a maximum. So this is the first maximum, and let's say, let me call m equal to 0. This is the second, m is equal to 1, and third, m is equal to 2, and so on. So same thing from this side. So this is m is equal to 1, and this is m is equal to 2. At the same time, we observe minima, and you will see that the minimum, let me change the color. Oops. The minimum, so here m is equal to, yes, 0 here. M is equal to 0 here. M is equal to 1, and we will see why I'm putting the m's here, okay, so that we these are, because we will have equations for these, okay. So you would not have an interference if the waves were continuing to travel in a planar wave. You will not have an interference pattern. So you have to have diffraction of light, meaning that the light will diverge at the slit in different directions. So this is what we call diffraction. And in that case, when you put a screen here, you'll observe a maximum at the center, and so on. Okay, so this is why we put a slit, in order to have this diffraction pattern, and the diffraction pattern will give us maximum and minima at the screen. Okay, so let's do the math. Okay, let's assume we have a planar wave with a wavelength lambda. It's arriving at the two slits S1 and S2. Okay, and when they diverge, let's consider point P here. And so this is distance R1, and this is distance R2 from the second slit. Okay, R1 and R2 as they are shown. Okay. And we want to determine what is the difference between the two paths. The difference, that's what we're calling delta, between R1 and R2. If the screen is far enough compare this, L is much larger than the separation between the two slits, if L is much larger, we can assume that as if these two these two rays are parallel. So if, for example, if I have my if I have my slits here and the screen there, the distance between the slits is very small compared to the distance L. So when they we can assume that the two rays are almost parallel to each other. And notice now this angle theta here is the same as this angle theta, and we can write that the path difference delta, which is R2 minus R1, is equal, so this delta over d is going to be equal to sine of theta. Okay, so the path difference delta is equal R2 minus R1 is equal d, which is the separation between the two slits, sine of theta. Okay, so what is the condition for having a maximum? In order to have a maximum, the path difference delta, which is d sine theta, has to be equal to have a constructive interference. D sine theta, which is the path difference, has to be a multiple of the wavelength, m lambda. So the delta, which is the path difference, has to be m times lambda, where m is going to be 0, plus or minus 1, plus or minus 2, and so on. Okay, so notice here m is called the order number. Order number does not mean it's the number of the fringe, because so remember, the first fringe is for m is equal to 0. The second maximum is m is equal to 1. So even though this is the second maximum, the first maximum is at the center, the second maximum m is equal to 1. So there is a difference between what's the number of the fringe and the order number. Unfortunately, m equal to 0 corresponds to the first maximum. Okay, m is equal to 1, go from one direction. It's going to be the second maximum, and minus 1 is going to be on the other side, and so on. So this is the condition. If we have this condition, then we will see the waves will arrive in phase. And when they arrive in phase, we will get the maximum intensity. That will we call constructive interference. Okay, how about the dark spots? Okay, the destructive interference, the condition for that, for the waves to be arriving out of phase, one will be opposite of the other one, is that the path length or path difference d sine theta, which is delta, has to be m plus 1 times lambda. Meaning, so here delta is going to be either 0 plus or minus lambda plus or minus 2 lambda, and so on. So this is what we have. Okay, here what do we have? We have the path difference is going to, for m is equal to 0, it's half of lambda. So it's plus m equal to 0. Yeah. So for m equal to 0, so it's half of lambda. So half of lambda. Okay. For m is equal to 1, it's going to be 3 lambda over 2. 3 lambda over 2, or minus or plus. For m is equal to 2, sorry, it's going to be equal to 2 plus 1 half. That's 5 halves. So it's plus or minus 5 lambda over 2. So notice, if delta is a multiple of lambda, 0, 1 lambda, 2 lambda, and so on, we get constructive interference. However, if the path difference is an odd multiple of lambda over 2, an odd multiple, so it's lambda over 2, 3 lambda over 2, 5 lambda over 2, then we get destructive interference. The waves will be arriving out of phase. Okay, so this is the conditions. So this is a condition for maximum or constructive interference, and this is the condition for minimum or destructive interference. So now we have a mathematical equation that is a function of wavelength, function of the t, the angle theta is what we see on the screen, and also for number. All right. Any question? So these you have to remember. These are the conditions for constructive and destructive interference, and you will use that for solving problems. So what is the analysis model? If we have a double slit experiment, okay, then we can determine that the position at point P, y over L is tangent theta. So y over L, as you can see here, y over L is tangent theta. So if theta corresponds to a bright spot, meaning delta, which is d sine theta, is equal m lambda, okay, then, so this is for a bright spot, okay, then y, the position of the bright spot, is going to be given, so y, in this case, is going to be L tangent theta, okay, so y is equal L tangent theta for the bright spot, and L is equal tangent theta for dark spot. So I can determine what are the positions of the dark spots and the bright spots, okay, from this. So if I know the angle theta for the bright spot and I have L, I can determine what is the position, okay, of the bright spot using this equation. Now, there is a simplification we can use. Since we said L is very far, if you are close to the center where the angle theta is small, for small angle theta we can use a small angle approximation where tangent theta is approximately equal to sine of theta. Small angle approximation. So assume L is large and we are only in this region. Let's say theta is plus or minus 15 degrees. So it's a small angle. For a small angle, we can do the approximation. Tangent theta is approximately equal to sine theta. So what we can do, we can replace tangent theta here by sine of theta, okay, because we have, this is the approximation, okay. Since tangent theta is equal y over L, we can now, for small angles, we can get that since d sine of theta for a bright spot is equal to m lambda, we can replace here tangent theta by sine theta and we can solve for y. So the position for a bright spot is equal L m lambda over d. So this is the position of the bright spots for a small angle theta. So this is why I put a small angle. This only is valid if you have a small angle theta. If you are far, like if angle theta is 30 degrees, then you would not be able to use. But you will see that even for 30 degrees, it's pretty good approximation. So, so that means if I have m equal to 0, what is the bright spot here? So it will be 0. So this is the first bright spot. First bright spot, but the m is 0. Okay? Let's go to m is equal to 1. So if m is equal to 1, that means the y bright spot is going to be equal L lambda over D. So L lambda over D, let's assume here. So this is the second bright spot for which m is equal to 1. So you can see the order number is different from the fringe number. So this is the first fringe, which is at the center. This is the second fringe. But the order m, the order number is 0 here and m here. Okay, let's do the same thing for the dark spot. So for the dark spot, we know y dark is L tangent theta, and we know that lambda is equal, d sine theta is equal m plus 1/2 lambda. So we'll replace tangent theta by sine theta. Okay, so this is for the condition lambda, delta, sorry, is d sine theta, it's m plus 1/2 times lambda. Okay, or m going to 0 plus or minus 1 and so on. And if we replace tangent theta by sine theta, we get this equation, which is the dark spot is given by this equation. And again, this assumes a small angle, meaning for small angle approximation, this is valid, that it's approximately sine theta, you can get the position, y position of the dark spot by using the equation. L times m plus 1/2 lambda over d. So notice now, this is a little bit different. So let me change the color. Oops. Okay, so let's do the dark spots. Okay, the first dark spot is when m is equal to 0. When m is equal to 0, y dark is going to be 1/2 lambda times L divided by D. So the first dark spot here, this is dark, for m is equal to 1. Okay, the other one from the other side is the opposite. Now for m is equal to 1, okay, the y dark is going to be L times 1 plus 1/2, that's 3/2 lambda divided by D. So the next, so this is for this one here, m is equal to 0. And for this one, for the next dark spot, m is equal to 1. So you have to be careful. The order of the dark and bright spots, the best thing is to draw it, and so that you remember which one has order 0. So for example, this is the order 0, m is equal to 0, it will give you the central bright spot. But m equal to 0 for the dark spot is not at the center, it's either on this edge or on this side. Okay, so please make sure you remember that the order number m is different from the fringe number on the screen. So these equations, you have to remember them, and you can use them for determining the position of the bright and the dark spot, but only when you have a small angle. If the angle is large, like 40 or something, then you cannot use this approximation, because sine theta in that case is not approximately equal to tangent theta. In that case, you have to solve without the approximation. You can still determine the position, but without using the approximation. All right, so let's do this. Why not? All right, so let me do a Kahoot. Okay. Okay, so join the Kahoot. Start. Yes, join the Kahoot, please. 593-4420. Okay, so I will start the question while you're joining. And you will have only 30 seconds to answer. So here, this is a little bit different from what you used to see before. Which of the following causes the fringes in a two-slit interference pattern to move farther apart? Okay, we have 11 correct answers, 17 incorrect answers, and some did not respond. Okay, I hope the rest of the students are going to be here for the quiz. Okay, all right, so let's see. So here, we want which following causes the fringes in a two-slit interference pattern to move farther apart. So what do we know? We know y, we know y for a small angle approximation, so I will use a small angle approximation, is equal to L m lambda over D. Okay, so let's see, and so y, so if for m is equal to 0, it's going to be y is equal to 0, but for m is equal to 1, y is just going to be L lambda over D. Okay, for m equal to 1. So what will make y smaller, because larger, because they are moving farther apart? Okay, decreasing the wavelength. If you decrease the wavelength, y will decrease, so that's not correct. Okay, decreasing the screen distance. So if we decrease L, the screen distance between the slit and the screen, y will decrease, so that's not correct. Okay, decreasing the slit spacing D. So if we decrease D, yes. Y will increase. All right? Now, immersing the entire apparatus in water is actually similar to decreasing, because the wavelength in air for a laser, for example, is larger than the wavelength of the laser in water. So it's very similar, but we did not study this because we did not have some of the earlier chapters of optics. So the correct answer anyway is C. All right? All right, so the analysis model we can use. The condition for bright fringes or constructive interference is d sine theta is m lambda, or m is equal 0, plus or minus 1, plus or minus 2. Remember, this is the order number, so this should be a semicolon here and also here. And the condition for dark fringes is d sine theta, which is the path difference, is equal to m plus 1/2 lambda, where m varies as 0, plus or minus 1, plus or minus 2. So this is what you need to solve problems. I mean, you need to remember these equations. All right? Let's do an example here. So here we are viewing a screen separated from a double slit by a distance L. So L is 4.8 meters. Okay? The distance between the two slits is D, 0.03 millimeters. Okay? There is a monochromatic light is directed toward the double split and forms an interference pattern on the screen. The first dark fringe is at 4.5 centimeter from the center line. So always you draw. So this is my first, let's assume this is my first dark fringe. So remember, for the first dark fringe, m is equal to 0. What is the condition for a dark fringe? We said lambda, or delta, sorry, is d sine theta for dark fringe is going to be equal m plus 1/2 times lambda. Okay, so the first dark fringe corresponds to m equal to 0. So m is equal to 0. So that means d sine theta is going to be equal to lambda over 2. Okay, so all right, the first dark fringe 4.5 centimeter. Or maybe I should use the other equation. Okay, so because I don't have the angle theta, they asked me to determine the wavelength, and I don't have theta. So let me use the other one. The other one, which is the position. The position. Let's assume a small angle. So I will assume small angle, and I can do that because notice L is much larger than D. Okay, and what did we say? We said for the dark Y dark spot is going to be equal L lambda m plus 1/2 divided by D. Correct? So, and for the first dark spot, m is equal to 0. So that means Y dark is going to be L times 1/2 of D, so, or L over 2D. L over 2D, because m is equal to 0. Correct? So I can get L lambda over 2D, and I can solve for lambda. So lambda is going to be Y for the first dark spot times 2D divided by the length L. And when you do that, you get the number you get is 562 nanometers. So we used the small angle approximation for the dark spot, and we used the fact that m is equal to 0, and m is equal to 0 here for the first dark spot, and we solved for the lambda. The next question is calculate the distance between the adjacent bright fringes. Okay, so let me erase all of this. Okay. Okay, so since they asked for the distance between the dark fringes, I can determine the distance between the first bright fringe and the one next to it. So for m equal to 0, remember the equation for Y bright spot is L times m lambda over D. Okay, the first here m equal to 0 will give me 0. Okay, for m is equal to 1, which is the next m is equal to 1, which is the next bright spot, I will get y is equal L lambda over d. So this is the distance. Since we have L, we determined lambda from the previous question, and we have d, we can solve for the distance. Okay, or you can do it in general. You can do it in general. So this is y for m. Y of m plus 1 is going to be L times m plus 1 lambda over d, and you do ym plus 1 minus ym, you get L lambda over d. Okay, and when you solve for that, you get the distance between the bright spots or the bright fringes is 9 centimeters. 9 centimeters. Notice we use the small angle approximation because this distance here, L, is much larger than the separation between the two slits, so we can assume it's a small angle. All right, next question. All right, so here is another question. A light source emits a visible light of two wavelengths, 430 nanometer and 510 nanometer. So it can be either this or this, not at the same time. The source is used for a double slit interference experiment in which the distance L is 1.5 meter and the distance between the slits is 0.025 millimeters. Find the separation distance between the third order, meaning m is equal to 3, bright fringes for the two wavelengths. So I just write the equation, okay, and again I will use the small angle approximation because L is much larger than the distance d, so L is much larger than d, okay, and so the third here will be somewhere here, so I can assume small angle, and I can determine this is a separation between the bright fringes. So y for bright fringes is L m lambda over d. So this is for one wavelength, and so this is for m is equal to 3. For m is equal to 3, y is going to be 3 L lambda over d. Now let's do it for the other wavelength. For the other wavelength, so let's call it y prime, we get also 3 L lambda prime over d. We want the difference between the two, the difference between the position of the third order bright fringes, so we can do y prime, which one is smaller? Let's do y prime minus y, so this is going to be 3L over d times lambda prime minus lambda, okay? And when we solve for that, we get the distance is 1.44 centimeter. So notice that these are not at the same time. You cannot have lambda and lambda prime at the same time. So you have lambda and you get fringes due to lambda, which is 430 nanometers. You determine what is the position of the third order fringe. Remember, the third order bright fringe, you start with 0. So this is the first order is here 1. Third order is m is equal to 3. This is the second order, m is equal to 2. The third order, m is equal to 3. But notice it's the fourth bright fringe if you count the one at the center. So it's 1, 2, 3, 4. M is equal to 3 corresponds to the fourth if you count the one in the center. Okay? So once I have determined the position for lambda, I can do the same thing for lambda prime and take the difference, and I tell you, okay, this is the difference between the third bright spots for wavelength of lambda and the wavelength of lambda prime. All right? Okay, so let me finish by this, the phase difference. Remember, we said if the two waves arrive in phase, or they arrive out of phase. What do we mean by phase? Okay, actually, the phase, you can get the phase difference between, let's say this is wave 1, this is wave 1 here, and this is wave 2 here, okay, and the delta is here, the phase difference, which is d sine theta. Okay, if we know lambda, delta, we can determine what is the phase difference. And we can actually use this equation. The phase difference between the two waves is equal to delta times 2 pi over lambda. So let's assume we have sine. One wave is A sine omega t. The other wave, so wave 1, okay, wave 2 is A sine omega t plus a phase difference phi. This is what we are referring to, the phase difference. The phase difference, if we know the path difference, which is delta, I can determine the phase difference. I just divide delta by lambda, which is the wavelength. Remember, one wavelength corresponds to a full cycle. Okay, if I divide delta by lambda and multiply by 2 pi, because a full cycle of a sine wave is 2 pi radians. So if I divide delta by lambda and multiply by 2 pi, I can get the phase difference between the two waves. Okay, so let us rewrite that. We know for constructive interference, delta has to be m lambda. 0 plus or minus 1, m0 plus or minus 1 plus minus 2. So let's use this equation and write what is the phase difference. We find the phase difference has to be m times 2 pi. That means the phase difference is 0 plus or minus 2 pi plus or minus 4 pi plus or minus 6 pi. So if the phase difference between the two waves is a multiple of 2 pi, including 0, then we have constructive interference because they arrive in phase. Okay? Now, if we take the condition for destructive interference, which we said delta is m plus 1/2 lambda, m plus 1/2 lambda with m0 plus or minus 1, we can use this equation and we get the phase is going to be difference is m plus 1/2 times 2 pi. Meaning, the phase difference for m equal to 0, 1/2 times 2 is 1. So it's plus or minus 5 for m is equal to 1. 1 plus 1/2, 3/2 times 2 pi is at 3 pi. So it's plus or minus 3 pi for m is equal to 2 plus or minus 5 pi. So the phase difference, if the phase difference is an odd multiple of pi, an odd multiple of pi, not including 0 of course, plus or minus 5, plus or minus 3 pi, plus or minus 4 pi, then the waves are out of phase, they will cancel each other. They will cancel each other and we have destructive interference. واضح? So, if the two waves are in phase, معناها the phase difference between them, phi, is going to be a multiple of 2 pi. In that case, we have constructive interference. So one of them is sine omega t, the other one is sine omega t plus 2 pi, well, plus 4 pi, and so on. However, if one is sine omega t, the other one is sine omega t plus pi, or plus 3 pi, or plus 5 pi, then they are out of phase. They will cancel each other. The two waves, they arrive, one is positive and one is negative, they will cancel each other. And we will have destructive interference. Okay, I hope this is clear. Okay, I will stop here because this is optional. I just put it for you to know the math. We can represent a light wave or a sound wave by this equation. Okay, and we can solve, but you can read it on your own because I have to start the quiz. Okay.